Okay, let's look at lesson 513. What's up with E? So, really neat number E here, and just how it occurs a lot in chemistry and calculus, just in nature in general. But let's discover this number and kind of how it helps us and kind of what it does with exponential functions. So, 26. Help. A scientist has discovered a strand of extremely aggressive bacteria. The bacteria currently cover 1 centimeter squared of the petri dish, and they know it's reproducing at 100% every day. Just meaning that it doubles every day, right? So it goes from 1 centimeter squared to 2 centimeters squared. But in the meantime, new bacteria have been produced. So those new bacteria will continue to reproduce, right? And so basically, they wonder, should they be worried that this is going to take over their lab? So let's just kind of work through this. So the bacteria double in size in a 24-hour period. But the new bacteria generated every hour. This means after 1 hour, 1 and 1/24 centimeter squared of bacteria, right? So that's what they're talking about using is this 1/124 raised to some t time, right? And so they'll continue to do that. Like, what if it's every minute? That would be 1/1440, right? Raised to the t, right? And so actually this t is 24 hours time t, right? This would be 140 times t, right? If we continue to do seconds, right, there's 86,400 seconds in a day, so 86,400 t, right? And then this goes on to I think sweet C says milliseconds, right? So 1/86400, and then we add three more zeros, right? And the same up top, 86400, and then three more zeros, t, right? So let's look at this and let's look at like what these actually get us. So if we look at our calculator and we go 1 and we go, can I do a mixed? So let's just do 1/24 plus 1. And we raise that to the 24th power, we get this 2.664. So this is really 2.664 to the t, right? If we do it again, right? So we go 1/1440 plus 1. And then we raise that to the 1440. We get 2.717. 2.7717 to the t. Okay, if we do it again, right? So 1/86,400 plus 1 raised to the 86,400. We get 2.718. 2.71826 to the t, right? And then the last one here, we got 1/86400, 123, right? Plus 1. And then we raise that to the 86400, 123, right? And we get 2.71828. 2.71828 raised to the t, right? And it says what would happen if it was continuous, right? And so continuous means that this is forever happening, or this number right here is approaching, 1, right? But as this approaches infinity, this approaches an infinite number. We approach this letter E, which is very, very close to this. It's that 2.718, right? So if we just do E to the first power, we can see there, that's what you get, that 2.71828, right? And that's what we're approaching, is that E to some T, right? Growth, right? So let's go back to the lesson here. So in the previous problem, what did you notice about the value of your base, right? It was approaching this E, right? So use a calculator to evaluate E to the first. We did, right? And it was very close to this 2.71828. So how many situations can you graph E? Again, it's an exponential function, guys. So like if we go here and we just graph like E to the X, um, right, it's still going to look exponential, right? So still, because your base number is just that 2.718, right? So very similar to what we've been doing and what it looks like. And so yeah. So now let's look at 28. A common application of this number is in compounded interest, right? Compounded why? Continuously. So from this number, this old formula we talked about in I think the first lesson, 1 plus r over n to the nt, right? So as this, right, approaches this infinite number like we just talked about, right, we get really close to just e, right? But our rate has to be in there somewhere. So it's e to the rt, right? So let's talk about this, right? So in countries where the inflation rate is under control, which is usually less than 20%, interest rates at banks stay low as well. However, in some countries, they have astronomical inflation rates. So, for example, in Zimbabwe in 2007, it was 2,200%. Assuming continuously compounded rate, right? How much will a $1,500 bag of groceries be? Right, this would be 2222, right? Yeah, as a decimal, right? Bag of groceries, right? So, um, so how much would this new value be in 1 month, right? Well, 1 month, T is normally in years, right? So 1 month would be, 1/12 would be this T value. Okay, so let's put this in here and see what we get, right? So um 1/12, right, times 22, right? And we do E to that number, right? So E raised to the 1.833, right? E raised to the 1.833, right? Is this 6.25 and then times 1,500, right? So we get that bag of groceries is now $9,381, right? So that new bag of groceries, $9,381, right? So it goes from 1,500 to 9,000. That's how much inflation was there, right? So in order to keep pace, banks often, offer interest rates that our bank might offer 100% interest on a deposit. So if they did that, and this one says they compounded it monthly, how much would you have, right? So if you said, hey, I deposited $500, right, it is at an interest rate of 100, which is, one, and it's compounded monthly, right? How much would you have in 1 year? So T is one, right? So let me put that in there, right? T is one, right? So let's do this, right? Let's look at this on a calculator. So we have um, 1/12 plus 1 raised to the 12th times $500 that we put in. We now have 1306, right? So we have our money is 1306. Well, the next question says, right, how much would you have if it was compounded continuously? So how does it change, right? If it's continuously compounded, it's obviously going to make more money, right? Our rate is 1 and our time is 1, right? So obviously this would just end up being 5 times 2.718, right? So let's see if we can do this. 500, whoops, 500 times E, or E to the first, times 500. That may be easier, right? It's 1359, right? So obviously we would make more money there if it was compounded continuously. So, right. And then this one says you're doing the same thing, continuously compound, approximate your answer using a graphing calculator. or your method of choice. So you're doing the same thing, right? Just plugging in or trying to find out doing this, but when will you get to 2400, right? So again, we're just approximating time. So you could, probably do, it's going to be 1 point something, right? So I'm just plugging in numbers there. And again, we're going to get to where we learn how to solve these exponentials. Um, so sorry, I didn't say this, but plugging in numbers for your t as in time, right? But we're going to get to where we can solve these later on in the chapter.